Hello, and welcome to Huff and Puff, my simple demonstration of the Hough Transform. If you haven't seen my guide on how the Hough Transform works, I strongly recommend you go back and watch it for two reasons. Firstly, the rest of this video will assume that you know what I'm talking about when I rattle off stuff about theta and p values. And secondly, my YouTube channel desperately needs the watch time. Needless to say, there's a link to that video in the description below. This JavaScript program lets you plot points on a pair of axes and then see how the Hough Transform identifies edges from them. In order to produce a program that gets through all the calculations involved in a reasonable time, the resolution of the program is rather low. This means that it will produce several spurious edges, a few false positives, but as always, the whole idea of the project is to give you a starting point for you to adapt into something a little more worthwhile. When you run the thing, here's what you see. To place points on those axes, just click the mouse somewhere on it and a small black square will appear. To remove the point, click on the black square and watch it disappear. Alternatively, there's a button to clear the entire grid. Once you have placed all the points you want, click on Perform Hough Transform to get the program to do its thing. Below the axes is a large white space. When the Hough Transform takes place, that white space is turned into one of those diagrams that we associate with the Hough Transform, with the sinusoid curves plotted in white on a black background. The sort of thing that I call a hair strand diagram. That empty white space is actually a canvas object in HTML5, which gets filled in with black and shades of grey later on. Underneath the canvas, and off the screenshot here, is a text area in which the results of the Hough Transform are displayed in numerical form. Since the transform is carried out by different pixels on the graph voting, in inverted commas, and this text area is responsible for announcing the result of that vote, I decided to call it Returning Officer. Well, what can I say? It was funny at the time. That pair of axes isn't just a couple of straight lines drawn on the screen. It's actually a table full of small square images, most of which are white, but a few of which contain lines. Here's how it's made up. An HTML table is created with the same number of rows and columns determined by a JavaScript variable size. Size tells you how many blanks there are in each quadrant. I've set size to be 30, so the table contains 61 rows and 61 columns, the extra one being for the axes themselves. For convenience, I set the variable s2 to be twice the value of size plus 1. There are 4 basic square graphics, each of which is 6 pixels by 6 pixels. The simple white square is called p0.png. The squares that make up the two axes are called x-axis 0.png and y-axis 0.png, with the single square representing 0.png. The 0 at the end of each of these graphic names means that the square is basically white, i.e. no edge points at that position. When the user clicks on any square, the graphic is replaced by an identical one, except that the white bit is coloured black, and the name ends with 1 instead. Since the size of the grid is determined by a JavaScript variable, the grid has to be drawn using JavaScript. The code that you can see is embedded in a table tag in HTML. I've had to compress some of the lines to make it all fit on one screen. A double for loop is used to display all the cells of the table, with the rows being enclosed within tr and /tr tags. The variable pic holds the name of the graphic file. Each cell is given a name, which is the letter P followed by the column and the row with an underscore between them. At the end of the block of code, 2 variables xRange and yRange are set up. More on these later. Each image is also given an onClick function, which calls the function pic, passing the column and row value so that the cell can be identified. When the user clicks on the graphic, the program stores the fact that the cell now contains an edge point and changes the graphic so that the 0 is replaced by a 1, i.e. the square turns black. Each point that you can click on that pair of axes is stored in a 2-dimensional array called G for grid. A nested loop is used to create S2 rows, each of which has S2 columns, and set each cell to 0 to indicate that the point has not been selected. The function pick takes two parameters, the column and row of the cell in question, and changes the corresponding value in G from 0 to 1, or vice versa. This means that clicking on a black selected point will deselect it again. The rest of the function is concerned with changing the graphic on screen. It does this by taking the file name associated with the graphic, i.e. the src property of the image, and replacing the 0 at the end of the file name with 1, or vice versa. Easier said than done, as it has to strip away the final 5 characters from the name, which is the 0 or 1 plus .png, and then add on the new value, 1 or 0, and the .png again. This is the new src property of the image, which updates the appropriate square on the screen. There are other global variables, of course, many of which only become relevant much later in the program. You'll remember that the Hough Transform is based on voting, with a grid of points, no, not the same grid as the axes you've just seen, contributing votes. These votes are stored in an array called votes. There's a surprise. We'll make that a two-dimensional array further down the line. A threshold is set up to determine whether any given set of points actually corresponds to an edge. I've picked an arbitrary value of 5 for this threshold. If you've ever seen the Hough Transform shown in graphic form, you'll know it consists of a large number of wavy lines, all crossing each other. It's the crossing points that signal the possible edges. However, as the number of lines increases, the number of crossing points goes through the roof. They can't all represent the equations of true edges. A crossing point is found when a particular combination of theta and p scores more than one vote. The more votes it scores, the more points lie in a straight line. And at some point we say, yes, we found enough points to indicate that they really do form an edge. I've chosen that number to be 5. The voting array must contain 181 columns. The horizontal axis on the voting grid corresponds to the values of angle theta, ranging from -90 to +90 inclusive. Including 0 in the middle, that's 181 values. The vertical axis plots the p values, and I have arbitrarily set that at 100 values. Now, I can't know in advance where you're going to put your edge points, so the program can't predict what the p values will be. It will be a waste of time for me to set the vertical axis of that grid to run from p equals 0 to p equals 99, only to find that some of the calculated p values turn out to be negative, for example. The problem is overcome by calculating all the p values for any given set of edge points, find the range of those values from minimum to maximum, and then slice up the vertical axis of the voting grid into 100 slots, based on those minimum and maximum values, which will be stored in global variables pmin and pmax. Two variables, xvals and yvals, are set up to hold the list of edge points selected while the Hough Transform is being performed. It is perfectly possible for the program to scan through all the points on that pair of axes, looking for the few cells that have been set to black. But the program will need to do this several times, and it's going to be a real drag, particularly since only a small percentage of those cells will have been selected. It's far more efficient, before the Hough Transform is performed, to read those few cells as pairs of coordinates into a list, which the program can simply work through. That's what xvals and yvals are for. The number of points is stored in variable numpts. The last few lines define the dimensions for the canvas that will hold the hair strand diagram. Instead of plotting each point on the canvas as a single pixel, it's less of a strain on the tired old eyes if it appears as a small square. The variable pixel_size is set to 3 to indicate that each pixel, in inverted commas, is actually a 3x3 square. The canvas is given the name visual on the screen, and it is associated with the variable canvas in the JavaScript program. Any change of this variable will be reflected in a change on the screen. The canvas itself must be set to 181 pixels wide to cope with all the theta values, and 100 pixels high to cope with all the p values. Of course, since each so-called pixel is actually pixel_size pixels on the screen, these dimensions are multiplied by pixel_size before being set. You'll notice that there are no numbers on that pair of axes, so it's impossible to tell what the coordinates of any selected point are just by looking at it. There are two text boxes on the screen for specifying the x and y ranges for the axes. The default values for each of these is 3, meaning that both axes run from -3 to +3. You can change either or both these values, and they don't have to be the same value, of course. For instance, if you change both these values to 10, then both axes run from -10 to +10. The magic happens when you click on the Perform Hough Transform button on the screen. This calls the function doHough, which splits the task into manageable chunks. Firstly, values of x range and y range are read from the text fields on the screen. There is no check that the text fields actually contain numbers, and you might like to remedy that by adding in some checks to prevent the program from producing nonsensical results. Now, I hear you ask, if the x range and y range values are just now being set, why were they defined in that JavaScript segment above, the part where the table rows were created? Well, I hear myself reply, those lines of code were used to set up the default values in those text fields in the first place. After that, doHough calls the following functions in short order. GetPoints translates those black spots on the grid into a list of numbers. FindPRange runs through the Hough transform not to cast votes, but simply to find the range of p values that it produces. Then the Hough transform proper is carried out by a function vote, in which the votes themselves are cast. The final two functions called are responsible for displaying the results on the screen. Function DrawVisual creates the hair strand diagram with all those wavy white lines on it, showing the crossing points. Then function ReportResults displays the equations of the resulting edges in the text area. Now we tackle each of those functions in turn. Function getPoints goes through each point on that grid looking for values in the array G that are set to 1. Whenever it finds one, it is translated into a pair of coordinates in x vals and y vals, with numpts being increased to track the number of points found. This is where the values of x range and y range are needed. In fact, it's the only point where they're needed. You won't hear me mention them again. Function findPRange sets the value of pmin and pmax to the minimum and maximum values of p that are produced given the points on the graph that you have chosen. Each is set to a dummy value, which can't possibly be the minimum or maximum required. Then when a more suitable point is found, the values of pmin and pmax are changed. A pair of nested loops is needed to get these extreme values. The outer loop goes through all the points in the list, with the inner one going through all possible theta values from -90 to +90. The actual calculation is performed by function getP, which turns a given theta value for a given point into a value of p using the trig functions built into JavaScript. These require angles to be in radians, so theta is turned into a variable called rad inside the function. Function vote is where the Hough transform is carried out for real. We now have the minimum and maximum values of p, so the votes can be cast for real, safe in the knowledge that they will all fit in the ballot box. Firstly, all the votes are set to 0 in the votes array for every p value and every theta value. Then each edge point is taken in turn. For that edge point, a p value is calculated using getP, as we did before. A row is found corresponding to that p value by finding how far through the range from pmin to pmax it is. The round function then turns that proportion into a row number, and the cell corresponding to that theta value and row number has its vote tally increased by 1. Two things to note here. Each row in the array votes cannot correspond to a precise value of p. Since there are only 100 rows in that array, the best we can do is to divide up the possible range of p values into 100 equal slots, with each p value calculated falling between two boundaries. Inevitably, precision is sacrificed. Of course, this problem is lessened if you increase the number of rows to, say, 1,000, at the expense of massively increased runtime, but it's a problem that never goes away entirely. Secondly, the theta values start at -90, so the column corresponding to any particular value of theta has to have 90 added to it. Theta equals -90 gives column 0, -89 gives column 1, and so on. Function DrawVisual creates the hair strand diagram from all those points you've chosen, turning each into a wavy white line on a black background. As you can imagine, it's quite convoluted. In fact, each of the lines is shown in various shades of grey, where darker points indicate fewer votes and lighter points indicate more. In most Hough Transform diagrams, the crossing points are displayed as brighter, and that's the effect here. In fact, I've gone one step further and display any cell with a number of votes equal to or greater than the threshold in red. As such, it is necessary to find the maximum number of votes that any candidate received, so that the range of brightnesses from 0, totally black, to 255, as white as you can get, is divided up suitably. This value is stored in the variable max. Then we go through all the points in the votes array, this time actually deciding what colour to plot them. If the number of votes is at the threshold or greater, it's simple. The point is to be pure red, shown by setting a variable red to 255 and a variable others to 0. You won't be surprised to learn that red indicates the red component of the point, and 255 is the maximum value, whereas others indicates the green and blue component, and 0 means no thank you. If the number of votes is less than the threshold, then both red and others are set to the same value, indicating a shade of grey. The exact shade is found by calculating what proportion of the highest vote this particular value is. If the highest number of votes cast for any cell were 10, for example, then the cell containing 5 votes will produce a shade of grey that is half the saturated value, half of 255 being just under 128. A test is carried out first to see if the value of max is 0, which happens if you click on the Hough button before specifying any points. Some people do, in which case the point is black. This avoids a division by 0 error in the program. The last two lines in the nested for loops do the actual drawing by filling in a square of the appropriate colour and pixel_size pixels along each side in the canvas at the appropriate position. Here's the sort of thing you get. You can see that I have carefully lined up my 10 points in 2 neat edges, which should give 2 nice, neat red points on the hair strand diagram, one for the horizontal line and one for the diagonal line. Is that what we get? Well, not exactly. In fact, we have 3 red points. 2 of them are at the left and right edges respectively. These 2, in fact, correspond to the same edge, the horizontal one. Horizontal lines can be represented by 2 combinations of p and theta. For the first, theta is plus 90 degrees, and for the other, theta is minus 90. The 2 values of p are the same, except one is positive, the other negative. Since our values of theta go from minus 90 to plus 90 inclusive, both of these will just squeeze onto the diagram. This does make sense in a mathematical way, as any horizontal line that has values, say, theta equals 90 degrees and p equals 2 units, could also be represented equally well by putting theta equal to minus 90 and p equals minus 2 units. It'll give you the same line. Here's another problem. The more points that you have in a straight edge, the greater the chance that the votes contributing to that edge will miss their marks slightly and be cast for adjacent candidates. This is a result of the imprecision with our p-values that I mentioned earlier. Here's another diagonal edge, this time with several more edge points than the threshold needed to recognize it. The result is that the curved lines do not cross in an exact pinpoint, and several very close cells gain enough votes to exceed the threshold. When we display the equations of the edge calculated, we will find that there are a few spurious equations generated, but with very close p and theta values. The last function in the program calculates and displays the equations of the edges determined. Report results is similar to DrawVisual, except that it deals with numbers rather than coloured squares. This slide shows the outer part of the function. The code where the equations are calculated lies where that row of dots is. More on that in a moment. The function goes through all the votes, looking for any of them that have met or exceeded the threshold. If so, it is a winning point, and is turned into an edge equation. It also keeps track of how many winners there are, and if no point hits the threshold, it displays a message that no one has won the election. The results are built up in the string variable s, and the last thing the program does is to copy this into the text area called returning officer. Here's the meat and potatoes of the calculation. The function dp2, which you see peppered all over that, is simply a function that displays any value passed to it to 2 decimal places. I shan't bore you with the details of that, it's only 1 line long anyway. Remember, at this point, we have already discovered a winning combination, given by the values of rho, which is basically the p-value, and col, which is basically the theta value. Well, not quite. To get the theta value, we have to subtract 90 from the value of col, and we have to turn rho back into at least an approximation of the correct p-value, with a formula that compares it to the range between the minimum and maximum possible p-values. But we get to p and theta without too much trouble. It's a simple enough step to add a line to string s that reports both these values, p equals such and such, theta equals such and such. And we could, of course, just leave it there and move on to the next winning candidate. However, most people don't think intuitively of straight lines in p-theta form. They prefer gradient m and intercept on the y-axis c. So we turn p and theta into those as well. We need to use the trigonometrical functions in JavaScript, so once again, theta must be converted into radians, and variable rad makes another appearance. It takes only a modicum of mathematics to rearrange the equation p equals x cos theta plus y sin theta into the form y equals some gradient x plus or minus some number, and you can crash through it for yourself on the back of an envelope. The calculation involves dividing by the sine of theta, which might be 0. Sine theta is 0 if theta itself is 0, which occurs for vertical lines. In this case, the equation is given differently, in the form x equals whatever p is, to 2 decimal places, of course. Other than that, the equation is presented as y equals gradient times x plus intercept. The variable sine, spelt with a g this time, is used to ensure that the equation is tidy, and we don't end up with a plus sign followed by a negative number. Here are the equations generated for the examples I've shown you. As predicted, the horizontal line did produce 2 equations, which turned out to be the same in gradient-intercept format. The first one occurred when theta was minus 90 and p came to 0.31. The second, when theta was plus 90 and p came to minus 0.31. It seems strange that a horizontal line would produce a negative p-value when theta was plus 90, but there is an explanation for it. I'll leave you to ponder it for yourself, but here's a clue. Remember that in the grid of black and white cells, the variable rho increases as you move down the screen, not up it. However, both of these give essentially the same equation, namely y equals minus 0.31. Minus? Really? Well, it's the same reason as before. Effectively, that set of axes is actually upside down. It's an Australian set of axes, if you like. The diagonal line gives the equation y equals x, which is what you would expect. It gets messier for the other diagonal line. You will recall that this gave us 3 winning points, all very close to each other. Inevitably, it also results in 3 equations, each with very similar values for the different parameters. And there you have the program. As you can see, it performs the basic Hough transform, but very crudely, and the results it gives are by no means as precise as we would like them to be. I'm sure you can find combinations of points that give sizable red blobs for the crossing points on the diagram, and result in a whole list of spurious equations being generated. The most obvious suggestion is that you try to increase the resolution of the p-values. You'll find that this leads to the code taking an age to run, and JavaScript losing patience and displaying a "your web page is taking too long to run" error message. As you've seen in previous projects, however, there are ways around this. Also, the editing facilities are a little primitive. You might have noticed that I included a button to clear the grid of points, but that's as far as it went. I suppose a more sophisticated means of placing points on the graph might not go amiss. However, that's where this particular program bows out and leaves the ball squarely in your court. I would be interested to hear how you improve the program in the comments below. Also, if you think that this video deserves a like, please do click the like button. Thank you.